All right. This is probably us. The floor is yours. What questions you got for me? Go ahead.
Okay. I made a list of all the questions I have.
That's good.
So the first thing I have is I'm confused on like bond angles and how to tell like which structures correlate with specific bond angles.
Okay. So for the purposes of an exam, I'm not going to hold you to the decimal points or the small differences, right? What you need to know is that a tetrahedron or a tetrahedral carbon is going to have bond angles of 109.5 degrees. Now, some tetrahedral atoms may have 108, some may have 110. You can vary a little bit, but that's usually what we consider it. A trigonal, planar. So anyway, this would be sp3, okay? This would be sp2, and they're going to have bond angles of about 120 degrees. So when you look at C, you know, these bond angles here and here and here are going to be around 120 degrees. Okay. And then for a linear carbon atom, which is an sp, right, it's going to be 180 degrees. So when you're talking about carbon-carbon triple bonds, right, these bond angles between here are going to be 180 degrees. And so you probably learned in Chem 106 that you've got lone pair, bonding pair repulsions and all that. And that's all true. I mean, if you can tell me trigonal, tetrahedral, trigonal, planar, and linear, I'll be happy.
Okay.
Does that make sense?
It does.
Good. What else?
I had a question from chapter 4.
Okay.
It's specifically problem 19, chapter 4. And in that problem, it's talking about, gives like the incorrect name for a certain organic molecule with an alkene. You have to give the correct name. So my question is, on part D of that problem, I forgot, is it 3,3-methyl something, right?
Part D?
Yes, sir.
It says 3,3-dimethylpentene.
Right. So my question is, where would you know where to put the double bond if
Well,
you're just given that?
That's one thing you don't exactly know, right?
Right.
So pentene, let's just assume, since it doesn't list it, that it's going to be a carbon number 1. And so 3,3-dimethylpentene. And they say that that is the incorrect name, right?
Right.
And so I think if we look at it, let's see what could be wrong. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 5. So it's not the length problem. I think it really comes down to the location of the alkene, right? So it probably should be, let's see, we want to number through the double bond such that it has the lowest numbering system, right? So I would say that this would be 3,3-dimethyl-1-pentene.
So if it's not given, just assume it's always at the first carbon?
Yeah, I would, yeah.
Okay.
Yeah. That would be the more accurate way to list it. Any others?
No, sir.
Go ahead.
Okay. So chapter 2, confused me the most of all the chapters, and I think it's because I don't fully understand how to tell when an electron is given or when it is received for acids and bases.
Okay.
I think.
All right, so if we think about the most basic reaction of taking H plus and reacting it with hydroxide to give water. This is the simplest acid-base reaction we can have, right? And we know that there's lone pairs of electrons on oxygen. It has a formal negative charge. We know that hydrogen doesn't have any electrons. And so to draw that mechanism, we would push a pair of electrons to hydrogen to make a bond between that oxygen and hydrogen. So this is donating its pair of electrons, which it formally owns right here, to hydrogen, which formally owns none, to make that bond. This bond right here. Okay. This bond already existed in this. Okay. So that's where the electrons, where they're going. What are some, do you have any other examples that maybe are? Let's take something simple like ammonia plus HCl. Which one of those is the acid and which one of those is the base? On the left.
HCl
Is what?
is the acid.
Yep, so this is going to be our acid. So this must mean this is our
Base.
base. And bases always give the electrons, right? So it would be that giving the electrons to the hydrogen, and then the electrons that are between the hydrogen and the chlorine would go on to chlorine to make the chloride. So this is donating its pair of electrons to the hydrogen atom. Hydrogen doesn't have a pair of electrons. Right? It's sharing a pair here, but it doesn't have a pair to donate. So it's accepting them.
So I identified the acid based off of the fact that it started with the hydrogen, but I think that is Bronsted method to identify it like
Yeah,
that.
Bronsted.
So if I were to know that that was an acid based on the Lewis mechanism of identifying, how would I do that?
Sure. So let me give you another example. Let's suppose we're going to react methanol. Well, let's make it dimethyl ether. This is a real reaction. Don't worry about the name yet. And we're going to react that with trimethyl borane. Whoop. And this is a Lewis acid, Lewis base reaction. I'm not going to show you what the product is. You tell me which one you think is the Lewis base, and you tell me which one you think is the Lewis acid based on the structures that I've drawn.
I think the acid is the first one.
You think this is the acid?
Yes.
And why do you think that?
Because of the lone pairs of electrons.
Okay, so if it's got lone pairs of electrons, then it has pairs that it could potentially donate, right?
Oh, yes.
So does that make it the acid or the base?
That would make it the base.
Okay, so probably this is the base.
Okay.
Why would this be the acid?
Because boron in the center doesn't have 4 bonds, it only has 3.
Okay, and why is that important? Where does boron sit on the periodic table? Which group, which period is it in?
It's in 3. Or,
What's in the second period, right? Period
Oh,
runs
oh.
horizontal,
yes.
right? Yeah, it's in the third column over, not counting the transition metals. That's true, right? And we know that everything in the second period would like to have an octet.
Yes.
Would like to have an octet, right?
Yes.
But boron only has 6 electrons around it. Well, 8 minus 6 is 2, so it could accept 2 electrons, and 2 electrons is a pair. Right? So we could have this reaction that occurs. make that. And that's a real reaction that happens.
I understand that now. Thank you.
Yeah.
That helps.
But no hydrogens in any of them that could be considered acidic. So it truly has to be explained with Lewis acid, Lewis base theory. What else? Any questions? Yeah.
One of the hallmark problems, it was 423.
423.
I think that was the only one in chapter 4 that I had started to
Take a look at it here. Oop. 423 says, which alkene can exist as a pair of easy isomers for each alkene that does draw both isomers? All right, so there's a series of alkenes that are listed, and we'll go through them here. So the first one is CH2 double bound to CHBr. When looking at that, it's very difficult to see whether or not you can have E or Z as it's written. It's written in more of a condensed structure. So what I recommend you do is actually draw it out. So I know I got two carbons connected together with a double bond because it's an alkene, right? This carbon has two hydrogens attached to it. This carbon has a hydrogen and a bromine. So when we're trying to determine if something is E or Z, we have to determine priorities on the carbons, right? Well, I can determine priorities here. Bromine is clearly higher atomic number than hydrogen, right? So this is going to be high priority. This is going to be low priority. But I can't assign priorities here because hydrogen and hydrogen are the same. So this cannot be an E or Z alkene. It can only exist in this structure. If I swap these two things, it's the same thing. If I actually swap these two things, it's actually the same thing. If you built a model of this and then built a model where you switched the position of this hydrogen, this bromine, you would see that they're the same thing. You couldn't distinguish the two. So there are no E and Z isomers.
Okay, I think it was just because of the way it's written out. So,
Yeah, you need to draw them out as individual things. Now let's look at B. So again, I'm going to draw it out. So I know that this is an alkene. There's my two carbons. And I know this carbon has a hydrogen and a CH3. And I know that this carbon has a hydrogen and a Br. Right? Again, high priority, low priority, low priority, high priority. The highs are on the same side, so I drew which one? This is the Z alkene. If I swap any two of these groups, I can swap this one or I could swap that one. I'll have exactly the opposite. So I think it asked you to also draw the other one. So I'm going to just leave the first carbon alone. Whoops, excuse me. It's a CH3. And just swap the other two. And again, now we've got low, high, low, high. There's my plane. The highs are on opposite sides, so this is the E alkene. Does that make sense? So needing to draw them out a little bit in 3 dimensions where you can see them will help you out with that. What else?
I have a question about Newman projections.
Okay.
And like, so if we're doing the thing, we have to like try to look down a certain bond for the Newman projection. How would we know if we're actually drawing it the way it's being represented, if that makes sense?
Yeah, so if I told you, take butane and look down the C2, C3 bond,
Right.
you would have to draw your butane, you would have to number your carbons, and you would have to know how to look down that. That's my eye looking down that bond, right?
Right.
So if I'm looking down the C2, C3 bond, that's indicating to me that carbon 2 should be in front of me, carbon 3 should be behind me. So that's the Newman projection that I need to draw. So this is going to be my dot, this is going to be my circle in the Newman projection, right? So I've got a dot, I've got a circle, right? And on the dot is going to have this CH3 coming straight down. And then that carbon also has 2 hydrogens attached to it, so that has to be on the other 2 sticks, if you will. My back carbon, which is the circle, has this CH3 pointing up, and then it also has 2 hydrogens attached to it, which have to be on the other sticks. So I know that I'm looking down, there's carbon number 2, I'm looking down that carbon 2, carbon 3 bond.
I guess my question would be like, how would you know whether or not it's like eclipsed or staggered just from looking at it? On like say you're given like the butane, it's like tell whether it's to be eclipsed or staggered. That's my question. Like, how could you tell from like looking at and drawing like that?
Drawn like what?
It's like the line model. How could you tell from that if it was supposed to be eclipsed or staggered?
Well, I mean, I can look at that and see, since my 2 methyl groups are on opposite
Right.
sides of that bond, that it has to be in the staggered,
formation, right?
anti-staggered conformation. Yeah. Chances are, what I'll do is I'll give you a bunch of Newman projections and ask you something about them.
Mm-hmm.
Which one's the least stable, which one's the most stable,
Okay.
which one's eclipsed, which one's anti, which one's gauche. I can ask any number of those questions. But usually I'm going to give you the Newman projection to make that analysis. Ouch. Got zapped. What other questions we got?
I have questions on the homework, 4.15.
415? Okay.
So it's a trans 2-methyl-3-hexene,
Mhm.
and I was wondering how to draw it. Like, I know how to draw like the line structure thing, but I don't know how to draw the structure.
Okay, so let's see what it wants. Example 4.1 and 4.5. Does it want me to provide? Just trying to clarify. Something real quick. If I can find the page. Yeah, so they're just asking you to draw out the bond line drawing is really what they're asking. They're not asking for the actual formula. They're just looking for the bottom line.
See, it said on the thing, it said draw the structural form.
Yeah, I know that's what it says. And so the structural formula is just how many carbons, how many hydrogens, but that's a molecular formula. But really what they mean is the bottom line drawing. So can you do that?
Yeah.
Okay, so you're good then.
I actually have a similar question on that problem. So it says, I forgot, it's a trans 3-methyl, right?
2-methyl-3-hexene.
Okay, so my question, whenever I got that homework, my question was, how do I know whether or not it's trans? Like, what is it trans to, is my question.
Yeah, well, that's always the thing about cis and trans, right? So let's look at that. So trans, 2-methyl-3-hexene. So let's figure it out. So I always start with the parent. Hex is going to be how many?
6.
6. So I'm going to have 6 carbons. So there's 6, right? And at carbon number 3, I'm going to have my first, that's what the first carbon's going to be. So is it going to be between 3 or 2, or it's going to be between 3 and 4, right? So 1, 2, 3, 4. So there's my alkene, right? And then I know that on carbon number 2, is that right? Trans 2-methyl? Well, yeah. Right, and so what's it trans to? It has nothing to do with the methyl, right? So you probably made the same mistake. I was thinking, well, the methyl's not going to be on carbon number 2. But it is, because that's perfectly fine. The trans has to do with the fact that you've got a hydrogen here and a hydrogen here, right?
Okay.
So this group and this group are both the high priority groups, and they're on opposite sides of one another.
Okay.
Right, we could have just as easily drawn it like this. Which would have been cis,
Right. Okay.
2-methyl-3-hexene. But I kind of took care of it in my original drawing with the zigzags. We're going to give you that kind of automatic. So this is trans. This would be cis. And this is the one that you were looking for. What else?
This is more of a general question, but I know when I was trying to practice with finding which molecule was more polar, I was having to like look up the electronegativity. Will electronegativity be given to us?
I will give you a periodic table that has the electronegativities under the elements. So you'll have, the periodic table, and, let's just say, here's fluorine, right? And underneath it, it'll say 4.0, so that you'll know that fluorine has an electronegativity of 4.0. And then every element underneath it will have that number underneath the element that will tell you what the electronegativity is. And so what you'll do then, if I gave you a bond, H and F, you'd be able to look up the electronegativities and determine that where the polarity lies. So I'll give you the electronegativity values. Having said all that, you should know the general trend, right? So sometimes you really don't need to look at a table to really know that there's an electronegativity difference. But I'll give it to you. So yeah, your front page of the exam, you'll tear off, that's your zip grade form. The second page is the honor pledge that you'll sign and print your name, and then on the back of the honor pledge is the periodic table, so you'll always be able to refer to that for anything that you need to have those values. Yeah. $25 questions and 1 bonus.
On example 1.12.
Example 112.
Yes. I think I was just kind of confused on how to do all the things it was asking on that specific example.
Okay.
I think the arrows confuse me. I think that's.
The red arrows?
Yes.
So what that's doing is telling you the bond angles around everything. So it asked you to draw out acetic acid, right? And they drew it out like this. And I think they put in the lone pairs. Yeah. And so then they asked you to identify the hybridization, it looks like, and then the bond angles. And so I have a carbon atom that has 1 pi bond, right? So that has to be what hybridization? Yeah, so that's sp2.
SP2.
The oxygen is also sp2 hybridized, and so they showed you that. This carbon has no pi bond, so it has to be sp3, right? This oxygen has no pi bond, so it has to be sp3. And then they're showing that the bond angles here are 109.5. 109.5 around here. Even though I drew that that's not drawn to scale. The bond angles around the sp2 are 120. And so that's what all of those values are. And then they said that these were sigma bonds, and this was a sigma bond and a pi bond, and it showed you what all the bonds were.
Okay.
So that's what those different arrows are trying to show you. Does that help?
It does, thank you.
What else you got? Anything else? Don't forget about the first part of chapter 5, basic reactions.
I actually have a question about that. Where did I write down? Are things like stereoselectivity going to be on the exam?
No, the only thing that we get close to right now in this part of the exam will be Markovnikov's rule.
Okay.
We've talked about that. So keep that in mind. You need to know what happens The reaction types that we covered, so things that we can add to alkenes. You need to know why alkene reactions are so, or addition reactions are so favorable. We talked about that, and you read about that. Know what you can add across an alkene at this point. You can add HCl, HBr, HI. You can add H2O across a double bond. We talked about a couple of different methods of doing that. And then we also talked about adding Cl2 or Br2 across a double bond. So you need to know those reactions. And they're all addition reactions. Technically, they have different reaction mechanisms. We talked about reaction mechanisms. I actually told you that there'd be a reaction diagram on the exam where you had to identify what something was on it, so make sure you review that. Right, so starting materials, products, energy of activation, transition states, intermediates. You need to be able to look at a reaction diagram and identify that. And so if we had a diagram that looks something like this, right? This is starting materials. These are products. This is an energy of activation. And this is an energy of activation for, oops, somebody's calling me. Who's calling me? Give me just 1 second. Hello? My dad and I usually talk late in the evening, and so when he calls early, I'll tell him to get grandma down here. So, my grandma's still alive, she's 96 years old. You never know when I could do that call. So I apologize for that. Transition states, right? Both of these are transition states. This in the middle would be an intermediate, right? So I could ask you any of those types of questions about any of that. You're going to have some type of reaction diagram. May or may not look like that one, but be able to identify those different pieces of a reaction diagram. What else we got? Know your functional groups, now that I'm on that page. Right? Be able to identify functional groups. At least the ones that are available to you now. So functional groups that we talked about were ketones and aldehydes and alcohols and amines. So all of those are fair game. Anything in chapter 1 that are listed there are fine. So table 1.9 has 7 of the common functional groups. I would know all of those. Carboxylic acid, amide. Those are going to be there. Those are fair game. Chapter 2 stuff, make sure you know acidity and basicity, Lewis acids, Lewis bases, identifying them. Being able to predict things based on, what pKa means, that kind of stuff. Chapter 3, of course, we start talking about alkanes and cycloalkanes. You're going to want to focus on naming. You're going to want to focus on what they can do, right? Basically, alkanes, you can burn them. They come from crude oil. We talked about, or at least you read through all of that stuff. Know how to name them. remaining in mind. Newman projections, of course. I'll probably limit the Newman projections to simple alkanes for the time being. You know, nothing crazy, nothing like some decane structure or something like that, just something simple. Remember that your cycloalkanes, like cyclohexane, takes a chair conformation and it can flip back and forth a little bit. And big groups usually like to be which way? Equatorial, that's right. So we have axial groups and we have equatorial groups, and the bigger groups almost will try to always be equatorial for the most stable. So that's good. Don't forget about the first day of class where we talked about some of the history of organic chemistry and some of the basics of Gen Chem that you needed to know. A little bit on equilibria. Talked a little bit about that. Know your hybridization, be able to identify hybridization. That's important. It'll be important to be able to tell me whether or not a carbon atom is sp3, sp, or sp2 hybridized. So keep that in mind. Of course, your cis-trans isomerism.